So do y'all have any questions for me before we begin today's lecture? And we're going through approximate analysis this week. And as I mentioned on Monday, these are techniques that you will be applying to the final project. So, and the topic that we're going to start today, the portal method, that's going to be a big part of the final project as well. Portal method is, as you'll find out, it's something that is pretty tedious and takes some time to work through. So that's why I said for your last homework assignment, which I will release this week, it will be due the week after Thanksgiving. I will give you the answers for at least for the portal method problems so that you can check your work as you go. But I encourage you to definitely go through it and make a genuine effort on your own to work through this process so that you're familiar with it before you have to complete it for your final project, right? So again, homework 9 is due Friday. I extended that deadline for y'all, so give you a little bit more time to work through the influence lines, because I know that is a topic that can always be a little bit confusing and difficult to wrap your head around when you're going through it. But do you have any questions for me on influence lines today? Okay. All right, good deal. As a reminder, there's plenty of example problems on D2L related to influence lines for you to reference as well. So, all right, so today we're going to talk about the portal method. This is a method specifically for analyzing the response of a frame to lateral loads, right? And specifically for moment frame. So I'm going to emphasize a few things here, and it's important to remember this. Do not, when you are applying the portal method, do not include vertical loads, right? Even if you have vertical loads on your frame, ignore them for the portal method, right? We're going to treat those vertical loads separately using the approximate analysis methods that we talked about on Monday for frames, right? So portal method, only lateral loads. You do not include vertical loads. If you try to include vertical loads, it will mess up your calculations. So again, lateral loads, that could be wind, seismic, etc. And when we say that this is for frames, that's specifically for moment frames. All right, so why is it called the portal method? Portal refers to a specific type of moment frame, right? If you think of, right, the word portal, it relates to a doorway, an entrance. So you see these portal frames often as entrances to ranches, right? You just see the wood portal frames there. And that just kind of, it's where it originates from. So since we're dealing with portal frames, which are moment frames, we assume that we have rigid connections between the beams and columns. So first we'll consider just this single story, single bay frame that's pinned at the base. Is this frame, as shown, is this determinate or indeterminate? Determinate? Why do you say it's determinate?
Like pin joints at the bottom, rigid joints up top.
Yep. So it's got pin joints at the bottom and rigid joints at the top, but can you find all the external reactions just using equilibrium? Yeah, because you have 4 reactions, 3 equilibrium equations. So it's indeterminate by 1 degree. And remember, the whole purpose of approximate analysis is to make simplifying assumptions that allow us to treat indeterminate structures as determinate structures for our initial estimates, right? So for frames, I'm going to show you what we end up doing, right? Remember what we ended up doing for the beams in the last lecture? What assumptions did we make?
We made them simply supported by cutting them away from fixed supports.
Right, and what assumption led to us being able to do that? Hinge. Yep. Yep, so we placed a hinge in the beam, and how did we know where to do that? It was based on the deflected shape, right? And we made a guess, an educated guess, as to where those inflection points would be in the beams. And then we can treat those inflection points as hinges because they both have the characteristic that moment is equal to 0. So we're going to take a similar approach for the frame, right? So we will consider a lateral load applied at the top of this frame. What will be the deflected shape? Since it's pinned at the base, right, those columns, they can rotate, so they'll lean. They'll lean in the direction of the applied load. And because we have rigid joints between the beams and the columns, right, remember those rigid joints have to maintain 90 degrees, although the joint itself can rotate. So that's going to look something like this. All right, and in order to meet that rigid joint condition, make that a little bit cleaner. That beam has to flex, right? So you end up with this S shape in the beam. So there will be an inflection point in the middle of that beam, right? Now, the assumption that we're going to make is the exact location of that inflection point. We know there's going to be an inflection point, right? But we're going to assume that it's exactly at the midspan. And again, since the inflection point has the same characteristic as a hinge, where moment is equal to 0 at that location, we can treat that location as a hinge, and then that makes our frame statically determinate, so we can break it apart, and knowing that m is equal to 0 at that location, we can find the internal forces, external reactions, and so on. But now let's take a look at a more indeterminate frame, all right? So if we have a portal frame where the supports are fixed at the base, how many degrees of indeterminacy do we have now? 3 degrees indeterminate, right? So we're going to need 3 inflection points. And if we consider the deflected shape of this frame, right, with the fixed supports at the base, the columns cannot rotate at the base, right? So they have to start out flush, 90 degrees to the base. But the frame will still sway in the direction of the load, right? Because the rigid joints are free to move and rotate. So this one's harder to draw, but it's going to look something like this, where you have an S shape in the columns as well as in the beams. All right, so the columns will bend and lean. And you'll have an inflection point. Let's see. The way I drew it, it's really kind of somewhere around here. All right, you'll have an inflection point in the columns and in the beams. All right, so we need 3 IPs, we got them. Let's say the columns lean and bend, and the beam bends. All right, so skipping down to this sentence here, right? I'm saying that in portal frames, the inflection points tend to occur close to the middle of the member, all right? This portal method for approximating our response assumes that the inflection points are exactly in the middle of every member. Now for beams, that inflection point being exactly in the middle is true. That's where it actually is going to be. For the columns, though, it's going to be a little bit different, and it's going to be even different from how I drew it. In columns, the inflection points will tend to be in the top half of the column. But again, for the portal method, we'll assume that they are exactly in the middle. So here we have the expanded free body diagram of this portal frame, which with 3 hinges now is determinate, right? So we can break it apart at the hinges, and by doing that, we can figure out all of the unknown forces. So here we're looking at, we have the reaction forces at the base, right? And we have our shear forces, which are the vertical forces in the beam and the horizontal forces in the column. And we have our axial forces, which are horizontal in the beam and vertical in the column. All right, so that takes care of all of our internal shear and axial forces, as well as the external reactions. But we're also going to be interested in knowing what are the end moments at the rigid joints, right? Because even though we know the moment will be 0 at these hinges, which we are placing at mid-span, they're not going to be 0 at those rigid joints, right? Because those rigid joints have to transfer a large moment from the beam to the column and so on. So over here, I summarize the information related to moments. All right, we know moment is 0 at the hinge. We're going to have a maximum moment at the ends of each member. So in order to find what those moments are, the process is to break the frame at each hinge and solve for the internal forces and the external reactions, all right? So we've already kind of shown those. And then to find those end moments, you go one member at a time, all right? And the calculation for the end moment is the internal shear of that member times the distance from the hinge to the rigid joint where you're calculating the end moment. All right, so for most cases, that distance is going to be half the length of the member, right? And I say most cases because the exception to that is when you have columns that are pinned at the base instead of fixed. And we'll look at examples of both of those cases later on in this lecture. All right, so this lecture it'll take today and Friday to get through the whole thing. So we'll take our time and pace it so that it sinks in and we talk about all the relevant information, right? Any questions so far? Okay. Give it a second for folks who are writing down. Yeah.
So when you calculate the moment at a rigid joint, do you just look at one side of the frame, not the top end and the downward member, like the L shape, or is it just one member, or is it just
So what you'll find is if we were to do that for this frame, we would want to know the end moments of the beam, right? So in order to do that, since we're assuming that the hinge is located in the center, we only need to take one side of that, right? So we would basically cut the beam right here, and then we already have it broken at the hinge, right? So you would break that piece out. You know your shear force is P/2 here, and you know you're going to have an end moment, right? It'll be in the other direction to counter the effect of that shear force. So all you do is you sum moments about the hinge to solve for that end member, right? Or actually, I guess a better way to explain it, because if you sum moments about the hinge, then yeah, you've got internal shear to think about over here, right? So if you sum moments about the end of the member, then you just have that internal shear at the hinge times that moment arm to get your end moment. And it's going to be the same magnitude on the other side of the beam, right? So over on this side of the beam, your internal shear is acting in the opposite direction, so your internal moment will also be in the opposite direction to counter that. Or let's see, it's going to be, you're going to have a clockwise moment on both ends, right? So it's going to be the opposite sign is what I meant to say, right? So your moment diagram for the beam will be like a positive moment to a negative moment of the same magnitude. Similar for columns, right? So for the column, you only need to take 1/2 of that column to find the end moment. And in this case, that's already really done because you know the moment reaction here, right? So the moment at the top of the column is going to be a counterclockwise moment, also PL/4, okay? So the column moment diagrams are going to look like this. And we'll go over that later in more detail, but that's basically what it is. So yeah, so you only really need to calculate the moment once for each member, because it's going to be the same magnitude on both ends with this approximate analysis assumption. Right? Later on, we'll see that in reality for the columns, it's going to be a slightly different value at the top versus the bottom. Any other questions? Okay. All right, so now that we've considered a single story, single bay frame, we're going to gradually expand the size of our frame. We'll think about a single story, 2-span frame, right? So we have equal bays and a lateral load applied at the top of the frame. Now, how many degrees of indeterminacy do we have? 6, that's correct. Yep, so there's 9 reactions. We have 3 equations. all right? But we have a problem now, right? We have 6 degrees of indeterminacy, so we need 6 assumptions to render this frame determinate. But we only have 5 members, and we're not going to have more than 1 inflection point in a member, right? So we can only assume 1 inflection point per member. We have 5. We need 1 more assumption. So down here, I state what that is, all right? We assume that the interior columns will take twice as much shear as the exterior columns in portal frames, right? And this is based on the fact that those interior columns will take more shear than the exterior columns, and it will be roughly twice as much. If you have equal bays, right, you can see just kind of thinking through in terms of tributary area, for example, right? This column has twice as much tributary area as these columns. So that's a reasonable assumption to make, okay? So that is our 6th assumption, and that is all we need in order to render this frame determinate. And that will hold true no matter how many stories or how many bays you have, right? Even if all of the columns are fixed at the base, right? You will always be able to get the right number of assumptions based on 1 hinge per member and this assumption right here. Now, if you have members that are pinned at the base, then you don't have as much indeterminacy in the frame, right? In that scenario, we don't have a hinge in the columns that are pinned at the base because the hinge is basically down at the base with the pin support, all right? So that's how we'll treat columns that are pinned at the base. So down here we have a bigger frame example, right? And the process is very similar. If we assume that all the columns in a specific level are the same size, etc. So the general process, right, is to start at the top level and go story by story to the base. So after you have placed hinges where they're supposed to be, all right, and so notice every member has a hinge except for the columns that are pinned at the base where the hinge is located at the base. So I'll note here, start at the top. Go story by story to the base. And then down below, I'm going to note that if exterior columns are pinned, the hinge is at the base, so we don't add one to the midspan. Let's see. Well, that's exterior specific to this frame, so I'm just going to write in general columns that are pinned. I want to avoid confusion here. Columns that are pinned already have a hinge at the base. So they will lean. Not bend. And if they're not bending, there's not going to be an inflection point. So we don't put a hinge at the midspan. All right, so I'm going to demonstrate the process with the top frame, or the top of this frame. And then it gets pretty repetitive, so we're not going to go through this whole example, but I'll just kind of demonstrate the big picture. And then at the end of this lecture, this set of notes, there is another example, a smaller frame that is completely worked out already, I believe. We'll look at that later. And I'll use that to talk more about finding the end moments and drawing the moment diagrams. And then on D2L, there will be another example that's completely worked out with more commentary for you to reference. So that's what's coming up with the portal method. All right, so we start at the top level. The first step is to find the shear in the columns, all right? So I've got all of the dimensions noted that are relevant. We have the applied load shown at the top. And we're just we just broke this top part of the frame off and isolated that as a free body diagram. So to find the shear in the columns, that's going to be just summing forces in X. So we have the applied load P is equal to 8V. So V is equal to P over 8. All right, so those exterior columns will take a shear of P over 8, and the interior columns will take a shear of P over 4. Once you have found the shear in the columns in terms of the applied loading, then you go through and you break each segment apart, right? So you're effectively isolating each joint. You can kind of think of this as a method of joints for frames. So similar to method of joints for trusses, except now you have rigid joints involved, and after you find all the vertical and horizontal unknown forces at the hinges, you can go back and calculate what those moments are at the joints. So isolate each joint and apply equilibrium. So we'll look at first, and I always work left to right on these frames. Let's see what else I want to do. I'm going to go ahead and number these hinges for bookkeeping purposes. So I'll just go through and label them 1, 2, 3, 4, 5, 6, 7, 8, and 9. So first, we will have our 1, 2s. And this gives us, we have our applied load P. We have our shear, which is P over 8. And then we have our unknown forces. F1, F2, and V2. All right, so I'm going to use V for the shears and F for the axial forces. So then if we sum moments about the beam hinge, which is 2, we have P over 8 times 5 feet. All right, I can add that on our little free body diagram too. Is equal to F1 times 5 feet. So F1 is equal to P over 8 downward. So is that column in tension or compression? What do you think? That's correct, it's in tension, right? So the rules for determining that are the same as what we talked about for method of joints for trusses, right? If the force is shown acting away from the joint, then it's in tension. If it's shown acting towards the joint, then it's in compression. Then we can sum forces in X to find F2. All right, so F2 plus P minus P over 8 is equal to 0. So F2 is equal to, we got negative 7 P over 8. So that's 7 P over 8 in the opposite direction that we initially assumed. So is that tension or compression? Compression, good. All right, and as a gut check, it makes sense that our beam, that is immediately after the applied load, is going to be in compression since that load is pushing on the frame. And it also makes sense that the column on that same side of the frame is in tension, because if you think about what that frame is doing when it's being pushed, I should mirror what you're seeing, when it's being pushed left to right, that right, my right side, your left for you, right, that side's going to be in tension as it leans over that way. So just always a good idea to do a gut check on those signs, right? And then from summing forces in Y, we get the shear at hinge 2 will be equal to P over 8 upward. All right, now we're ready to move on to the next joint. So that's isolating at those 3 hinges, 2, 3, and 4. So we'll have, that's 5 feet and 7.5 feet. Oh, I drew an extra hinge. No hinge at the rigid joint. Oops. All right, so now we know F2 is putting that beam in compression, and that was 7P over 8. All right, so we already found that. V2, we're just transferring that equal magnitude opposite direction, so that'll be down on this side, and that's P over 8. We have our shear at hinge 3, which is, say, V3. You don't need to write that. We can just say that's P over 4. All right, and then our unknown forces, we have F3, V3, and that's V4 for hinge 4, V4, and F4. All right, so again, summing moments about the beam hinge, which is 4 in this case. We have P over 8 times 12.5 feet. So that's from the shear at hinge 2, minus the shear at hinge 3, which is P over 4, times that moment arm of 5 feet, plus the axial force in column 3, times a moment arm of 7.5 feet. So we get F3 is equal to P over 24 downward. All right, so this column is also in tension, but a smaller force, right? So that also makes sense, right? That the force will be smaller for the inside columns, the axial force. The exterior columns should be expected to take the greatest axial load in resisting that lateral force, right? Resisting that overturning. Then going through and summing forces in Y, we find that V4 is equal to P over 6 upward. And from summing forces in X, we get F4 is equal to 5P over 8 in compression. All right, so you get the idea. I'm not going to go through the entire frame. That would take longer than the time that we have in class. But we would proceed with this process all the way through the end of this top section of the frame, right? So total of 5 free body diagrams. By the time we get to this last joint here, all right, by that time we don't have, the only unknown that we would have would be the axial force in that column, right? Because we would know all the forces in that beam already. By the time we get here, we would just be transferring those over. So the only unknown would be the axial force in the column. But you always still want to check sum of moments about that joint, right? You can find that axial force by summing forces in Y. But still always check sum of moments. Let's see, yeah. It doesn't matter about which point, right? This last free body diagram, doesn't matter which point you want to sum moments about, but just make sure that sum of moments is satisfied, because it is easy to get a vertical sum of forces check that works out, right? As you know from other applications, other problems. But if the moment sum of forces does not equal to 0, that's a problem, right? We need to make sure that we have equilibrium against rigid body rotation. And in the portal method in particular, it's very easy to get through a row like this and then move on to the next row without recognizing that there may be mistakes because sum of moments didn't work out at the last joint, right? So that's a good way to catch mistakes before you move on to the next level. And you don't want to bring wrong numbers down to the next level, because then your whole frame, it'll trickle through, right? And you have to redo the entire thing. So always, always, always do a sum of moments check at the very end to make sure that everything is working out. And you don't have to do sum of moments on the whole, right, the whole section. I recommend doing sum of moments on that last joint, right, to make sure that everything makes sense. And if it doesn't, then go back and try and figure out where something went wrong. And this inevitably happens, right? Even every time I try to do a portal method problem, I usually find that I made some silly mistake along the way, and I need to go back and find that mistake before I move on to the next level. So I'm going to note down here, all right, we continue until all top level forces are found. And that's 5 total free body diagrams for this problem. And on the last joint at each level, sum forces in Y to find the column axial force. All right, then you've found all the unknowns, but still check sum of forces in X and sum of moments. Before moving on to the next level. And in your work, right, both for homework and also for the final project, I do want to see a free body diagram clearly drawn for every single joint, right, with the forces noted on there, right, known and unknown. So just, kind of be clear and organized in your work. Make sure that it's easy to follow, not just for me, but also for you and your own records in the future, right, or if you have to go back and check something. Making sure that your work is organized and easy to follow is beneficial for everybody all around. Yes.
Do you want the free body diagrams redrawn, like once you know which direction?
No, that's not necessary. Yeah. Yeah, thanks for asking. But it is a good idea, and I like to see, like for example, here, just in your answers, right, show the actual direction in your answer, and also if it's an axial force, indicate tension or compression as you go through. Okay. All right, so you would proceed to complete that level and then go to the next level. So there are two different approaches you could take when going to the next level. One is starting off the way I've shown here, right, where we're just cutting through the column hinges at that next level and isolating the top part of the frame. From there, you can find the new shear in the columns, right? So that would be, again, summing forces in X. Here we have 2P, right, because we have a P at each level, is equal to 8V. So V is equal to P over 4. All right, and then from there, you isolate each joint. So you've got the hinges in the columns above and below the joint and the hinges in the beams on either side. So you're gonna isolate those joints, have 5 free body diagrams. I'll sketch these in. All right, these colors. And you will go through and analyze those 5 joints. So this time, you're gonna have forces at this hinge, right, that you already know from the previous level. So you would transfer that information, right? In this case, we found F1 is P over 8 in tension, right? So when we go to this level, is that going to be acting up or down? Up, right. So that's going to be P over 8 in tension. I'm going to write this, let's see, I'll make that red, and I'll say, and then our shear too, right? We know the shear in the top level columns was, at the exterior column, was P over 8, but now it's acting in the opposite direction, right? So those are transferred from top level. And that's why it's so important to make sure that your top level forces are correct before moving on to the next level, because you use those top level forces in this analysis, right? So then you also don't forget about the applied force at that left side. And then you would have your shear, in this case, is now P over 4. And your unknown forces that you're solving for at those 2 hinges, okay? So you still just have 3 unknowns. You have the 3 equations. Find those 3 unknowns on this free body diagram, and then move on to the next joint, right? So that next joint will look like this. And then after that, you have another one like that, etc. At the very last joint, make sure that you check sum of moments and sum of forces in X, right? Sum of forces in X will be a little more obvious. Sum of moments is one that I definitely want to see you calculate out and show that you're checking that, right? And then go to the next level. So in this frame, the next level is the base, right? And so remember, if you have columns that are pinned at the base, they do not have a hinge at mid-span. So you don't cut them there, you don't put a hinge there. You keep the entire length of that column wherever it may be. And so you would isolate those joints like this. After finding the shear, I'll go ahead and find the shear. So summing forces in X, we have 3P is equal to 8V. So V is equal to 3P over 8. All right, and you have, that would be distributed here, where we would have 2V at the interior columns and 1V at the exterior columns. And I think, yeah, I already had that written above. And then go through that last level same way, right? Analyze the 5 joints left to right, and then check the sum of moments at that last joint. So I'm just gonna, once again, draw that first joint in this level. In this case, it's going to take us all the way to the pin support. So when you're analyzing the unknown forces down here, that's going to be your axial reaction, right? The vertical reaction at the base. So don't forget about the P, and you'll have your forces from above. And the unknown forces at the hinge. Okay, questions so far? All right, so at the top of this page, I said that there are 2 different ways that you could go about starting another level after you've completed one. The one that I've demonstrated, right, takes the cut through the columns of the level that you're now analyzing and first looks at everything above that to get the sum of forces equation. You can, if you want, you can also cut through the hinges above and below that level that you're focused on and transfer all those forces from above to those hinges that are now exposed, and some forces in X to get your shear in the columns that you're analyzing now. You should get the same results, but you know, it might be easier. I think it's a little bit easier to do it this way. So, but just so you know, you can always cut through hinges. It's just a matter of being strategic as to, do you need to cut through those hinges right now, or is it just making a little bit extra work for you, right? Okay, any questions? All right, well, this is a great stopping point. Next time we'll look at this example, which is almost completely worked through. So we'll go through the next part of the problem, which is then to find the end moments, and then draw the moment diagrams on the frame, okay? But this is a nice way to get a general idea of the magnitude of responses that you can expect to see in a moment frame due to lateral loads, right? Thank you all for your attention. I will see you on Friday. We're almost to the break. Hang in there.